Our explorations of the deviations from the IP network layer. The first one is fragmentation that we have seen last week. Let me continue fragmentation with a little question. Well, first this observation, which I already discussed last week, but is important to understand why fragmentation might occur. In principle, UDP, as we all know from the programming lab, has an interface which is message-oriented. So UDP provides a service that not only transports the bytes to the destination, but also transport them with the definition of where is the beginning and where is the end of a message. TCP doesn't do this, as you remember. As a result of this, UDP may allow to send at the service interface may allow to have blocks that are larger than the path MTU. That's a classical implementation of UDP, and all systems I've seen this happens this way. In particular, it's quite possible that the default maximum datagram size is 64K bytes. It can be larger if you tweak with the operating systems. So it's quite possible, if you write an application that generates a message, say, of 1,500 or 1,600 bytes, that it is fragmented at the source. It will then be reassembled at the destination. The benefit is done by the operating system, so as a programmer, you don't have to live with that. Now, if you have very, very large blocks, then it won't work. So you have a maximum to which that happens. With TCP, none of this happens. So in principle, with TCP, we avoid fragmentation. In principle. Now, you can't guarantee that every system will do it. Now, this being said, I'm not sure when we sniff traffic, is it true that the port number is always present in all packets? In all UDP packets? I looked at your answers in 5 seconds. And the correct answer is 2. Well, first we have to understand what a packet really means. A packet means what we observe on the line. If there has been fragmentation, a datagram may result in several packets. Now, what can happen with UDP? Well, the UDP header is at the beginning of the IP payload. So if the datagram is fragmented, the second fragment doesn't contain the UDP header. Fragmentation occurs at the IP layer. The IP header is repeated, but the higher layer headers disappear in the following fragments. So when you receive a UDP packet that is fragmented, you can't read a port number. Right? So if you try to read a port number, there will be something. There are bits and bytes usually, but they are not port numbers. Right? And this may happen with IPv6 as well as with IPv4, right? Which is a problem perhaps for NAT. Right? If you have a NAT that is trying to change the IP address by looking at the port number, then the NAT, in fact, will need to be aware of the fragmentation. One more question. TCP now. Five more seconds. Now you have the correct solution. Everything will be retransmitted for the same reason as before. So imagine here the second packet. So this TCP implementation has generated a TCP segment that's too large. Should avoid that, should be avoided, but assume it's not avoided. Then at router R1, the second fragment is lost, is generated, then lost somewhere. At destination, reassembly is done by the IP layer. So since the datagram is not complete, it's missing. So before passing it to the IP, to the TCP layer, the thing is lost. It's impossible, in fact. It's not just because of layering dogma. Of course, in software, you don't follow dogma. If you could avoid this loss, you would do it. But since here you have missing data here that is typically impossible, that has no TCP header, you simply ignore the reception of the entire datagram. And TCP will see the destination will not acknowledge anything of this block, so sooner or later it will be retransmitted entirely. This is precisely the behavior we would like to avoid, because when we miss one datagram, we repeat three. That's very bad from many viewpoints. So typically, I repeat, TCP is supposed to do path MTU estimation, estimates that on this case, router R1 is not able to forward such a large packet, and by doing the path MTU estimation we've discussed last week, and therefore should avoid doing this. Voilà, that's all we will see about fragmentation. Perhaps the take-home message is as much as possible, we try to avoid it. Some UDP applications may force your system to do fragmentation, but if you code a UDP application, it's a good idea to be aware of fragmentation and even with UDP, avoid it. Any questions on fragmentation? Then we move to IPv6 again. IPv4 fragmentation is primarily an issue with IPv4, though it can exist with IPv6. But with IPv6, remember, we mandate that the minimum packet size for any IPv6 implementation is 1280 bytes, which means that as an application, if you want to avoid absolutely fragmentation, just make sure you don't generate packets that are larger than this. Now, this will be very beautiful when we have IPv6, but now we have both. So we continue our discussion of how do we live in a world where part of the systems are IPv4 and part of the systems are not. So we have already started discussing this, and we have already discussed the difference between interworking and like-to-like access. Interworking is when we would like somebody speaking IPv4 being able to communicate with somebody speaking IPv6, which in principle is impossible because the packet formats are not the same. So if I send an IPv6 packet to a machine that is IPv4 only, what will happen? Try to do this. I mean, imagine you're building software that is trying to send an IPv4 packet to an IPv6 only machine. Well, it won't work for zillions of reasons, but if you try to make it work, you see a lot of problems. The first problem is which address do you give to the, you have to send it to a destination address. The destination address is IPv6, your IPv4. So what is the IPv4 address of an IPv6 destination? That's the first kind of problems. We will find that for all the interworking solutions, we will have those address mapping issues to solve. The other issue is, even if I find a way to put an IPv4 address inside an IPv6 destination address, which should be possible because there are more bits in IPv6 address space than in IPv4, so it should be possible. Even if we find a way to do this, we generate an IPv4 packet, ether type 41, then when we try to, when we send it over wireless or whatever network, it will have an ether type of IPv4. So when reaching the destination, if the destination is not IPv4 compatible, it will simply not receive it. So we have somehow to transform the packet from IPv4 to IPv6 in some form or another. We will see how to do this. We have already seen one solution for the interworking issue that solves the problem radically by saying we don't solve it at the IP layer. We put an application layer gateway that speaks both IPv6 and IPv4. And here Homer is transferring a file from a web server or an object of any kind. And if we put in the middle a web proxy that speaks IPv4 and IPv6, then Homer's PC is able to talk to that web proxy over IPv6, and the web proxy will act as a store and forward mechanism to speak IPv4 to the web server. We have seen that this works and is simple, but we do store and forward, so it's not a large-scale solution. If everybody needs to do that, we essentially need to duplicate the server infrastructure of the world, which is a bit expensive. Today we will see an alternative to this, which is the bare-bone translation, called NAT64. NAT, we've seen that concept already, is network address translation. We've seen it essentially in the context of private IPv4 addresses to public IPv4 addresses. Now we can do it also from IPv4 addresses, private or public, to IPv6 addresses, in principle public only. So the key word is translation. So if we have a NAT64, and if we have an IPv6 only machine and an IPv4 only machine, in this scenario, the classical scenario is IP servers are on IPv4, and then clients are on IPv6. This is very often one of the scenarios considered in the transition, with the idea that if you have a server that is already existing, then part of the world is IPv4, and then emerging parts of the world, new wireless networks, for example, might get IPv6 only addresses because they are in parts of the world where IPv4 addresses are no longer available. But you still want to be able to access the old stuff. Okay, so how does it work? Well, it works very much in the way we have seen before. It is as if the IPv6 internet would be a private IPv4 network. Addresses that don't make sense for the global IPv4 internet, but that do make sense locally here. So, for this to work, the NAT has to have an IPv4 address pool to translate the IPv6 address. What is this what is this pool of addresses? Well, let's see now. If, when we have a regular NAT, like your NAT at home on ADSL or whatever cable modem, you have a pool of address that is simply one address. That's the public address that's given to you by your provider. And all the private addresses that you have in your home are mapped to this specific address. Now, if here the pool of address means we don't give just one address, but perhaps more than one. Why more than one? Well, because at home you are not expected to have hundreds of thousands of computers, but just a few. So with one address and playing with the port numbers, different port numbers, we reuse, in fact, some of the port number space as extensions to the address space. But if you do that at a large scale, it won't work. So you need more than one IP addresses. That's why we have a pool of address. Okay. And now the philosophy is that to this machine, the host 4 will appear as an IPv6 address that will be translated, and vice versa. Just like when I am at home with my machine that has a 10 dot something address, to the rest of the world, I don't appear under the 10 dot something address, but an address, a publicly valid address. So here we'll have this, but now in both directions here, which is different from the NATs we have at home. Right? When I receive packets from the public internet at home through my NAT, the public address is not translated. Here, both will need to be translated. Yes?
What is the problem if NAT uses a single public IP and changes the port number for every client within the private network?
Well, the problem is the port numbers are also used for something. For their original purpose is to distinguish different processes and different sockets. Okay. So you have a port number is 16 bits. You can use in practice 4 bits of the port number space to use it for multiplexing. Okay. So if you have a very, very large number of systems, then you cannot use the port. You simply don't have enough port numbers. Okay. Because each system will use a number of ports already. Let's see how it works exactly. So in this example, I assume that the NAT pool is 120.130.26/24. So we have a fixed prefix of 24. That means we have 8 bits to 256 IPv4 addresses. So that means we have used 256 addresses of the IPv4 internet. If we don't have them, it won't work. And the entire IPv6 internet will be mapped to that space, right? Now, when a packet comes from the client here, the client has an IPv6 address, this usual long string of hexadecimal digits. Through IPv6 routing, it will go to the NAT. When it comes to the NAT will do the classical job. It says, here is the source address, as if it would be a 10 dot something, protocol type, port number. Then I will look for a combination of 4 available addresses and ports that are available. Now, the only address I can use, the only bits of the address I can use are the 8 low order bits that are here, and I pick one available port number. So this is the usual NAT stuff. So when the packet will reach the server has the illusion it's speaking to somebody that's on the IPv4 internet. Of course, while doing that, the NAT will need to change the IPv6 header into an IPv4 header, which is easy because in most cases, because the mapping is one-to-one, TTL is called hop limit, etc. But other than that, it's fairly easy to do. And we'll need to remember the mapping that was done. Okay. This is called stateful operation because we need to remember the mapping. We need in the table to remember that we have changed this address and this port to that address and that specific port. In the reverse direction, it's a bit simpler because IPv6 address space is huge. So when we map an IPv4 address into an IPv6 address, we can do subsetting. We can reserve one space of the IPv6 address space to put IPv4 addresses. So there is one block which is reserved, which is this one, 64FF9B, which is reserved for mapping IPv4 addresses in IPv6 addresses. So this block, I don't know why it has disappeared, which looks like a random block, is not a random block, is a well-known prefix, which means IPv4 addresses mapped to IPv6. /96, because 96 plus 32 equals 128, so these are those hexadecimal digits, a lot of zeros, and at the end we have space for 4 bytes, 8 hexadecimal digits that will be used for coding the IPv4 addresses. So if you recognize here, this is 192.021 mapped in hexadecimal digits, right? So this is exactly that address here. So the same thing will happen in the reverse direction. When this guy responds, this guy will respond to 120, 130, 26, 33. The packet will have source address, which will be, it will reach NAT2, the NAT at point 2, and then the NAT will translate using this rule. So that's the So, quick question to see if you followed this complex mode of operation. How is the v4 address, the server, H4 server source address, translated to a v6 address at the NAT here? So when the packet is translated, the source address needs to be mapped. How is this mapping done? Is it by looking at a translation table, an algorithm, or yet another method? Let's look at your solutions. And by a majority, but too short a majority, the correct answer is 2. It is algorithmic. Here the algorithm is trivial. It simply means concatenate this prefix with the address. Right? So for a computer it's straightforward. For a human being you need to change a decimal notation to hexa. But the computer does not even do that, right? For the computer, the address is already in bits, in binary form when it receives it, so it's a simple concatenation of this fixed prefix to this address here. So the packet, when it goes via this, we need to map 2 addresses, the source and the destination. Mapping the source address is algorithmic, from IPv4 to IPv6. Mapping the destination address is based on the table that we have learned before, because we need to remember that one. Voilà, this is how NAT64 works. Of course, there are still issues like how do I know which address I should use? How do I know when I am H6? Which address I should use to reach H4? Well, the answer is very simple. How do we know which address to use? It's via DNS. So NAT64 goes together with an extension of DNS called DNS64 that will cheat a bit by saying when the client here wants to connect to, for example, InfoScience epfl.ch, because this is an IPv6 only machine, it will ask for quadruple A records. It's not interested in getting an IPv4 address. It doesn't speak IPv4. So we'll go to the DNS and ask, what is the IPv6 address of that machine? If you go to a regular DNS, because this machine, H4, doesn't run IPv6, there will be no answer. Stop, end of the story, doesn't work, you can't reach the server. If you are on a network that supports NAT64, hopefully the operator, the administrator of the network, has also implemented a DNS64 server that will know that for all my IPv6 clients, I need to translate all the records that exist only in A form to a quadruple A form. So it is not the regular DNS server, it's the DNS server of this operator that will do this manipulation. Remember, DNS servers can be the authoritative sources, but they can be also caches. In bad countries, the caches manipulate things to make sure you don't get access to things the government doesn't want. Here, it is a more benign intention. We want you to have access to something that in principle you could not by giving you a quadruple A record. And this quadruple A record is also very simple to do for the DNS server because the mapping is trivial. We simply, when we do the request here, this DNS server will do the requests for the world. Now this DNS server has to be IPv4 and IPv6, at least able to get IPv4 record. You will try to get an IPv6 record. If it doesn't get it, then it will translate it as shown here by adding the prefix to this. So the client happily lives in his rosy IPv6 only world where everything works. So it will have the illusion that that server at the far end is IPv6 because it has an IPv6 address. And then it will send to that destination address, which will reach NAT64. So if we put things together, then this client will generate a packet to this mapped IPv6 address with its own address, and then it's IPv6 as usual. When it goes through the NAT, the header is translated, and the destination address is mapped here very easily by just looking at the end. And of course, the source address, that's more tricky. You do the regular NAT job by going to your NAT table, and you transform also possibly the source port. How do you transform, in fact, 120, 130, 26, 33 to the correct IPv6 address in the reverse direction when the server responds? So let's see your solutions. And now the correct answer, the majority size increases question after question, is of course using the NAT table. So we have seen the NAT operation, which is fairly simple. There's a number of other bells and whistles that we won't discuss, but they're easy to imagine. For example, how does the IPv6 cloud here know that this packet should go to a NAT64 router? Because after all, we're in an IPv6 world. There might be other servers that are IPv6, then the destination will go to these. By which magic are we sure that if needed, we go through the NAT64 router? Yes?
It starts with the 64 FF9B prefix.
Mm-hmm.
So this means that it's originally an IPv4, but the NAT translated to...
Yes, but if you have a large IPv6 internet here with thousands of routers, By which magic will you make sure that those packets that have to reach the IPv4 internet, they go to the NAT64? You need to do something in the network. With RIP, for example, if you run RIP in this network. Yes?
Tries to send it to someone and it's the address of no one, so it knows it has to go somewhere else.
Yes, but that's not the way we try to do things, right? When transporting packets, we don't try and see, because the routers are the bottleneck of the internet. We want them to go fast and know where to go.
Because NAT64 knows the pool of addresses it has, it could statically configure RIP because he knows the prefix and he knows the addresses, and it can announce it to the others.
Yes, so in RIP it would be called redistribute connected. So NAT64 will distribute into IPv4 internet with redistribute connected the pool of IPv4 addresses it has in RIP6, in RIP classical RIP. In the IPv6 internet, the same will be done. The NAT64 will do redistribute connected of which prefix?
0/0.
Not 0/0, that would be the default route. That would mean anything that we don't know where to route will go to the NAT64, which would be wrong, because there is a default route in the IPv6 internet. You might want to go to the switch interface to go to something that is IPv6, but not in your network. Well, this prefix. This prefix has to be injected into RIP-NG, RIP-v6, the RIP for IPv6 of the pink cloud by the NAT64. If you have several NAT64, each of them will inject it into this cloud. Therefore, all routers into the IPv6 cloud will know that if I have a destination address that starts with this block, which automatically means that's something that is NATed, something that has to go to one of those NAT64 router, and it will go to them. So we need to do those two injections in the two sides. And now, so we will always do that in all solutions for IPv4, IPv6 interworking. Now, it's always asymmetric. In the IPv6 world, it's very easy. Usually we reserve a block of addresses, that means the IPv4 world, and we inject it. In the IPv4 world, it's more nasty because we don't know which block to inject. So in that case, it's the block that is owned by this NAT, which has to be configured by every provider. The block that I gave here, 64FF9B, is the block that is by default allocated to NAT64. Some providers like Switch, they like to do the default values. Some other providers like the French Free, which is one of the leaders in IPv6 deployment worldwide, they don't like this. They want to control everything. So they typically use a block of their own, because they don't want someone else, if they advertise a block like this one, they don't want someone else, not a free customer, to use their 6.4 NAT. So they will replace this block by a block that is in the block of addresses owned by this operator. So in general, you might find different blocks than just this one. But this one is the one that is done by default for typically academic networks that like to stay with the default. We've seen client 6 to server 4. In principle, it works in the other direction. The other direction is the more nasty problem where you are a company that has only IPv6 addresses and you have web servers and you want people to reach you on those web servers. Well, first, if that really happens, perhaps you should try to still have a few IPv4 addresses for your web servers, because if you're doing real business with that, you don't want to take the risk that somebody cannot reach you because you're on IPv6 only. But if that happens, the solution works. But as with NATs, remember the IPv6 internet from the NAT viewpoint is like your private network at home. If you put a web server at home behind your NAT, you need to do something in your NAT for the NAT to know that there is a server, because remember the NAT randomly changes the port numbers. Of course, if you do that, if you have a server, you need to have a well-defined port number available to everyone. So you need to do some static configuration of the server address and the port number used by this server in the NAT, which is ugly. So in principle, you will not want to do it, but that's something that some people propose to do here. So let's skip those details. Now, what are the pros and cons of NAT 6.4? In particular, compared to the application layer gateway that we have seen before. Who wants to try a pro or a con? Any opinion? I mean, imagine you work for Swisscom next year, and they ask you, okay, we have to do IPv6 to IPv4 interworking. Should we do NAT 6.4 or application layer gateway? Yes?
It works on the IP layer, not the application layer. So it's, from the performance point of view, it's better than the gateway.
Yes, so from the performance viewpoint, from the kind of hardware you will need to deploy, a NAT is a router. It's not strictly a router in the sense it does things that are a bit weird. We're in the chapter deviations from the layer. But from the job, it's closer to a router than to a web server. It doesn't need multi-terabytes of disk space. It has more work to do than a router. It has to go through its table and do an exact match. But still, the packet is forwarded packet by packet. So in terms of performance, it will work better. And also, it's more transparent to applications. You don't, if somebody does a new type of application, you won't need to do your NAT, right? Are there any drawbacks? Complexity of implementing the NAT, sure, but you will buy it from Cisco or Juniper. Perhaps it's expensive. If you say it's complex, Cisco will sell it for more money than, okay. But is it complex from a deployment viewpoint? As long as you don't have servers on the IPv6 side, it's not complex, right? You need a pool, you need to manage the pool, you need to make sure you have enough addresses. It's not free, but it's less hassle probably than having a web proxy. A web proxy is very sensitive to the amount of traffic. If you have all of a sudden lots of people that download files that are huge, your disk space on the web proxy will be a problem, so you need to monitor it closely. Probably you have less of those problems here. So the main advantage is perhaps its transparency. And the main drawback is it's stateful, and in particular means that it's hard to support servers on the IPv6 side. But that's a solution that we expect to see deployed by many providers. In fact, any provider today who deploys IPv6 provides this service, practically, or any commercial provider. Voilà, that's the end of our first topic today on IPv4, IPv6. We'll come back to it with, because unfortunately, or fortunately for us, there are many ways, complementary ways of interworking IPv4 and IPv6. But before getting there, let's look at another weird deviation that is very often implemented, practically everywhere that has a Class B address, like at EPFL, so you can test this on the wired EPFL network. It's called proxy ARP. Proxy ARP is when you want to cheat. So everything we do in this chapter is we're cheating. We're cheating with IPv6, IPv4, we're cheating with packet sizes. Now we cheat with something really bad and ugly, but that's often done. It was originally often done because of misunderstanding of the IP principle, when you remember people say sometimes, or used to say in the past, and many continue to repeat today, that the EPFL block 128.178 is a class B block because it starts with 128, something between 128 and 192. If it's a class B block, it means the network prefix is 16 bits. Now, bad implementations of hosts will automatically say, well, if you have an EPFL address, your prefix is 16 bits. But at EPFL, we know the prefix is 24 bits. So what should we do? Well, we should configure all machines to use 24 bits, which is done with DHCP today. But in the past, it was not always done. Some people found a way to solve that problem by pretending, in fact, everything would work with such a prefix. Another way to view it is to say that assume you want to put an address at the wrong place. For example, that address here, 12.12.12.4, is on a wrong subnet. The subnet 12.12.12/24 is here between R1 and R2. And assume for some reason you want to put a machine that had this address behind R3. Principle, you should not. It doesn't work. The principle, one of the two principles of unicast IP says one subnet is one subnet prefix. So if you have this address, you should be there. In fact, in the exams, that's the correct answer, or in the quiz, right? Which is a correct mask here. But as usual, we can do incorrect things sometimes if we compensate the incorrection by doing a second incorrection here. The first incorrection is when a packet wants to go to the host here, we need to do something in the routers. Because if I send the packet to router R2, by default, if it sees such a destination address, it will put it on its left interface, which is the correct thing to do in principle. How can we solve it? Well, we can put a more specific route in this router, which is called a host route, where a host route is by definition a route where the length of the prefix is the complete address. For IPv6, 128, for IPv4, 32 bits. So if I write in the router R2 this address that for this destination I have to go here, then it will work at R2. But I will need to do it also at R3, because otherwise R3 by default will route it back to R2. So the first thing you will need to do is inject into your routing protocol one entry for each of the machines for which you're doing this, which in principle is okay if you have one or two machines, is less okay if you are managing your network with thousands of machines in this way. Probably that's not a good idea. Let's see here an example where things like this are deployed. This is an image of part of the EPFL network that's not so much used today, but still when everything goes wrong, the only thing that works is to use a modem over a telephone line to reach a modem server to reach a network. What is a modem? A modem is something that uses a telephone connection on which it puts the bits and bytes that are translated to voice signals. Right? So you can hear when you... So assume you do this, and at EPFL we have one box called SIG500CS, which is on the network, the Ethernet network 128.178.84. And you can call it, if I call it from the machine called GreenMac, you connect to the EPFL network via the telephone network. Because you do it via the telephone network, all the connection between you and GreenMac is very hard to intercept. So if somebody is trying to listen to the traffic, then it's very hard to listen to that part of the traffic. The police can, but otherwise it's very difficult. Now, if you do this, should SIG500CS be a router, a bridge, or an application layer gateway? Hint, look at the addresses. at your answers in 5 seconds. Good. It should be a bridge, because at EPFL we know the network masks are 24 bits. So if we do something that has the same LAN ID, the same subnet prefix on both sides, then automatically it's a bridge. That means it's the same LAN, right? That is what theory says and what grading in QCM says. It should be a bridge. However, at EPFL it runs as a router. Okay, which is a deviation topic of today's slide. We do a break, and after the break we will see by which magic we can make a bridge into a router.